Thin film coatings for protecting reinforced concrete bridge elements. Derek Castle, thin film coatings for protecting reinforced concrete bridge elements.
I'm Derek Castle. As you can see on the screen, there's four of us worked together to put this presentation together. And presentation really is a culmination of three research reports that span nearly 15 years from the beginning of the data to the last report. The first report there, the evaluation of deterioration of structural concrete due to chloride intrusion and other damaging mechanisms, the University of Kentucky looked at, or Kentucky Transportation Cabinet looked at a lot of bridges and saw that the concrete deterioration, beam ends, or not so much beam ends, but pier caps, abutment seats, was a lot of deterioration. And so they commissioned research to go look at a number of bridges and identify the chloride ion penetration resistance or chloride ion levels at pretty much mat depth at about 2 inches into the concrete surfaces. The second research topic was looking at remediation efforts, looking at traditional sealants, penetrant sealants typically, and then the third one is the thin film concrete coatings, which is inevitably the topic that we want to present on today. Look at the problem beyond the scope of the state of Kentucky. If you look at the NBIS inventory from the Federal Highway Administration, there's roughly 610,000 bridges in the U.S. You take in consideration that you break those into three primary components, decks, substructures, and superstructures, gives you about 1.8 million components, of which approximately 1.6 million of them are reinforced concrete. So as we look at deterioration issues in concrete, we see there's a magnitude of the problem with chloride ion penetration or soluble salt penetration into the porosity of the concrete and corrosion of the reinforcing bar or reinforcing strands, if you want, in pre-stressed concrete beams. Although there's a number of ways to quantify action levels for chlorides or salts in concrete, for the purpose of the presentation, we've chosen what we believe to be the most regularly used or regularly referenced values. That would be 0.03 weight percent, or percent chloride to weight of concrete will initiate corrosion, is enough to initiate corrosion of steel reinforcement. 0.08% chloride, you get accelerated corrosion of the reinforcement, and at or above 0.18%, you have a major section loss of the reinforcement. Back in 2002, the Kentucky Transportation Cabinet looked at a handful of bridge decks, primarily from the standpoint of we had used what we classified as a AAA concrete mixed design in the bridge decks, and there was some surface crazing, surface cracking that had taken place early on, and we wanted to look at how those cracks were allowing propagation of chloride ion into the deck. And so that study in 2002 showed that there was very little chloride ion penetration into those decks. One of the driving factors behind looking at it and being concerned with the deck cracking was that in the mid-90s, the Kentucky Transportation Cabinet had transitioned from being a reactive winter weather state to a proactive winter weather state, meaning that somewhere before the mid-90s, the state waited on the snowstorm or the ice storm to come and dealt with it as it was materializing and as snow or ice was on the ground. So all the salting activities and things were done post-accumulation. Somewhere mid-90s, early 90s, they switched to a proactive mindset where they would go out and pre-treat the roadways. And a lot of the times using a liquid de-icer, calcium chloride, and some of the bridge crews like to refer to the use of liquid de-icing chemicals as liquid bridge remover. So, but anyway, so by 2002, there hadn't been a lot of that was early on in the pre-treating scenario, so there hadn't been very much chloride ion penetration at that point. By 2011, the state had seen an increase in concrete deterioration, so the university went out and did a much larger study into chloride ion penetration into the bridge deck, into all three elements, the decks, the superstructure, and substructures. Testing was done again at about 2-inch depth, looking to see what chloride content was presumably at matte depth. It's a very busy slide, but what you can take away from this slide is, with all the sampling done, more than 50% of all more than 50% of all the samples taken were above the action level. So for chloride ion penetration, the decks tended to be the lowest because they're designed to drain. So if you get a better look at this graphic, and then the next graphic coming up will give you a little better indication as well, a little easier to read. The abutment seats and the pier caps are the most susceptible to deep chloride ion penetration, which makes sense. Most of us have joints that leak. That seems to be a relatively simple thing to fix, but hasn't proven to be such. So over the abutment seats and over the pier caps, we tend to have a lot of salt water, heavily laden salt water in the winter months going through the joints, and those structures typically aren't designed to drain well. They are fairly flat for inspection purposes and seating purposes. So you get a lot of ponding of salt water on there, and by simple nature of the porosity of the concrete, you get a lot of penetration. This is the same graph that you just saw, only it's just represented numerical instead of graphic form. And it shows that in the first column there, second column, the less than 0.03, you got the abutment seats are 56% of all samples from the abutments were around a 0.3. 18%, almost 19% were between the 0.03 and 0.08, so between initiation and accelerated corrosion. But you look at the very last column, the accelerated corrosion or major section loss at greater than 0.18 weight percent, the abutments are 20% of the samples of the abutment seat samples are greater than 0.8% chloride by weight percent by concrete or by weight concrete. The pier caps, almost 50% of them were around the 0.03 range, and in 40%, almost 41%, were in the accelerated corrosion range, 0.03 to 0.08. Again, just shows the leaking joints are truly provided as the pathway to deterioration of the concrete. Simply a picture showing spalling of concrete. We've all seen lovely pictures of those and drive under bridges all the time that look like this. So in the second study, after we did the study for identifying how bad the problem was, chloride ion penetration into our concrete structures, we looked at mitigation of that. What can you do to prevent further deterioration? What can you do to prevent further chloride ion penetration? And so the common thing at the time was penetrating sealers, silane, siloxane-based penetrating sealers. So the University of Kentucky did a study where they evaluated 24 of commercially available penetrant sealers, most of which were either silane or siloxane-based. And they ranged from everything from 4 to 7% silane to 100% silanes. Out of this data, only about a third of the commercially available products tested gave you reasonable, what I would consider reasonable protection. They gave you somewhere above about 75–80% reduction in chloride ion penetration. Now, the way the testing was done, it was laboratory testing, where they did the AASHTO T259, T260 testing, the chloride 90-day salt ponding test. So take a concrete block, coat it, and pond salt water on it, 5% solution salt water for 90 days. Clean it off, measure the depth of chloride of penetration at usually half-inch increments. So the conclusion of this study was simply better protection. You need better protection for the non-driving surfaces. I think the best performers gave you about a third of them, about four of the 24 tested materials gave you about a roughly 75% reduction. Another third of the group gave you somewhere around 40 to 50% reduction, and the remaining third of the group really gave you nothing. So the last study that makes up this presentation was looking at better approaches, better products, or at least different products that would give you a better solution to chloride ion penetration resistance for your concrete. So I wanted to identify thin film coatings, wanted to take a look at coatings that had minimal surface preparation requirements, minimal application time, that were user-friendly. There was an assumption made that state forces would be the primary ones putting these coating systems on. The criteria for looking at products, obviously we wanted products that had good adhesion to concrete, had good resistance to chloride transmission or chloride intrusion, wanted color and some color stability with some gloss retention for the aesthetics component. Ultimately, 8 systems were submitted and considered for evaluation. So generically, we had 2-component high solids, high build polyamide epoxy in a acrylic aliphatic polyurethane finish coat. Another high solids epoxy with a waterborne acrylic finish coat, a waterborne acrylic sealer, and an elastomeric high build acrylic finish coat. System 4 was ultimately withdrawn because at the time of submission, the manufacturer didn't make it well known that there was a 24-hour wait between the application and primer recoat. And so that once it was originally accepted, but once that was determined, the system was dropped from the testing program because it was seen as not applicator or field friendly. So system the 5 was a methyl methacrylate acrylate copolymer. System 6 cycloaliphatic amine epoxy and a acrylic polyester finish coat. 7 was a waterborne acrylic and was 2-coat acrylic system. And then 8 was a castor oil gypsum coating system. This study had 2 components, had the laboratory component as well as a field component. So the systems were evaluated in laboratory conditions for color and gloss retention as well as the 90-day salt ponding testing. And then the cabinet gave the university a section of a bridge that had under a joint that had a sufficient amount of pier cap and pier standards for coating application in the field. In the laboratory, this is a picture of the concrete block specimen for the 90-day salt ponding testing. As you can see, the bug holes, the assumption was made that this would be more closely resemble real life, that the coating application was not 100% pinhole free because didn't expect that contractors or maintenance forces were going to achieve 100% coating coverage, that the films were not going to be pinhole free simply because of the porosity and the texture of the substrate trying to coat it. Looking at adhesion, the field adhesion, we had a range, which is typical when you're evaluating concrete coatings. You tend to get a much wider range of adhesion values because of the substrate. The important part of the slide is essentially the right-hand side, the failure mode, where nearly all the failures were cohesive in the concrete, so cohesive in the substrate. As long as your coating adhesion is as good as your cohesive strength of your substrate, that's about as good as you can ask for. In the laboratory, again, we have better control of the concrete specimens, better control of the surface preparation. So you got higher film or higher adhesion rates, but again, these were predominantly cohesive failure of the substrate. Compiling data, going back to the research that was done on the 24 penetrating sealers, looked at chloride ion penetration in 90-day salt ponding test at the 1/2 inch depth and 1 inch. And the primary reason that looking at 1/2 inch is simply time. The test is only for 90 days. So we would look at the top 1/2 inch and then look at the neck at 1 inch and look at to get comparative data between the ability of penetrant sealers to reduce chloride ion penetration versus the thin film coatings. So this is at 1/2 inch. You can see that many of the systems are probably 0.1, 0.08, 0.1 chloride by weight percent concrete at 1/2 inch in 90 days. So the very low bars there, the ones, which one's the pointer here? The very low bars, that's obviously the couple, 4 systems of penetrant sealers that gave you a high percent reduction in chloride ion penetration. This is the same set of data, only at 1 inch depth. So again, you have a very limited number of products that are staying below the 0.03 threshold, or the very lowest performers are still up nearing or above 0.01, nearing 0.02 weight percent in 90 days in 90 days at inch deep. Contrast that to the chloride, to the thin film coatings. There were 8 systems submitted. The zero system, what's labeled as zero, this is the uncoated and ponded block. So this gives you your baseline. So the concrete itself, which the concrete mix design or matrix for the 2 studies were very similar. But so in this one, we've added the other slides were just so busy because of all the data. This one felt like we had room to show you just what the concrete itself did. So the concrete mix design, at a 1/2 inch in 90 days, you had 0.13 chloride by weight percent. At 1 inch, you were at basically 0.03 at the action level in just the chloride itself. So of the 7 systems tested, remember we took out system 4 because of the recode issue. You have 3 systems that gave you noticeably better performance than the other systems. Looking at color retention, I guess back up, the 3 systems here that show you the lowest chloride ion penetration, those are better than 90% reduction in chloride ion penetration. And that was, again, on blocks that there wasn't a wholesale issue, a wholesale intent to fully coat the blocks when you had the pinholes. So there's no way you're going to get 100% reduction because you got some chloride going through the pinholes. But those 3 gave you better than 90, I think we were up 94, 96% reduction in chloride ion penetration on those 3 particular systems. Color and gloss, not a lot of delineation in color retention, the delta E, the color retention, other than system 8, which if you remember was the castor oil and gypsum. I don't think there was a lot of hope to have good color retention in that system to start with, just based on the technology, but it bared itself out. It went from gray to brown real quick. Gloss, again, most of the systems, from color and gloss standpoint, there's really not a huge delineation between any of these products. They all did really well other than the castor oil system. So this slide just simply is it's a condition ratings, and it pairs together the proposed cost over time. So if you're, it's when structure is new, you're looking at, this is cost of maintenance versus time. When the system is in good shape, when the structure itself is in good condition, relatively new, it doesn't cost as nearly as much to do preventive maintenance. Whereas if you wait till the MBI condition ratings start to drop and the overall performance of the structure begins to be compromised, then it becomes more and more expensive. Most of that's due to surface preparation, the labor intensive portion of it. Dotted line here is looking at the cost of treatments. If you are looking at scheduling of events or prioritizing maintenance, the sooner you can get to structures, the sooner you can get to them to do preventive maintenance. If you're not building in the coatings and things to protect your concrete from the time you put it out from construction, the sooner you can get to them from a maintenance perspective, the less it's going to cost you. This is a barrier wall that was an original field trial of a number of concrete coating systems. Section of the wall, some parts of the wall were pressure washed, others were abrasive blasted and had multiple coating systems put on them back in 2004. One of those coating systems was the same system that was used in the latest study, the 2016 study. And so it was an epoxy and urethane system. So there's a couple of different data sets that go to that particular system that has shown good performance, a good track record over time. In the study, the adhesion really didn't become an issue. All the coating systems showed significant adhesion to bond to the concrete and give you long-term performance from an adhesion standpoint. Systems 1, 2, and 6 had performed, from the graphic, showed significant increase in performance from chloride ion penetration resistance. Each of those 3 systems have a commonality of having an epoxy primer. So 2 of them are epoxy with urethane, and the other one is an epoxy with an acrylic top coat. I think the takeaway from this presentation, from the research that was done in this presentation, is the industry for decades has looked at penetrant style sealers, especially for bridge decks and other concrete structure and other parts of concrete structures, as the industry standard for how you seal, protect, and preserve concrete. At least based on this study, looking at 24 commercially available products, most of which have quite long track records of being in the industry, there's only a small handful of them that give you significant reduction in chloride ion penetration resistance. So your likelihood of picking one of those particular ones that has a high chloride ion penetration resistance, it's a gamble. So are you picking the right one? In addition, even if you get the really good ones, you're looking at somewhere 75 to 80% chloride ion penetration resistance. If you look at thin film coatings for your non-traffic bearing surfaces, at least, you wouldn't want to put the thin films on traffic bearing. They'll be slick. So for non-traffic bearing concrete, the thin film, there's a myriad of, from the results of this study, you're looking at primarily epoxy-based products and then urethane finish coats, maybe even acrylic finish coats for touch-up and ease of maintenance long-term. Those products should have the ability to give you much higher chloride ion penetration resistance, greater than 90% reduction in chloride ion penetration, as well as long-term performance. And the other thing I like about the thin film coatings are their topical treatment. So if they disbond, if something happens to them, if they get mechanical damage, you have a way to recognize that. You can see it in an inspection. You'll note it, you'll find it, and you can go out and do spot repairs to touch it up, much like we talk about in steel coatings. With penetrant sealers, one of my primary issues with penetrant sealers is you don't know they're not working until you have spalling concrete. And at that point, you've got a much larger repair bill in front of you.
In looking at your chart of when to do that maintenance, I think one of my cohorts says the right work at the right time or the right maintenance. For these sealers on concrete structures, is there a point that you've already defined that it's not beneficial, cost-effective to apply it? Let's say we have a bridge with a footer and we know the chlorides are at the steel, but it hasn't spalled yet. Have you determined if that's still a benefit to apply it? Will it kind of freeze everything in place, or is it too late by the time the chlorides reach the steel to try to do any coatings?
Well, in order for corrosion to occur for the reinforcing, it's the old acronym ACME. You got to have the anode cathode metallic pathway and an electrolyte. So even if you've got chloride embedded into the concrete, if anything you can do to mitigate or reduce the amount of moisture that gets into the concrete, then you can, to some degree, minimize the level of the activity of the corrosion cell, just simply by controlling moisture. Obviously, the sooner you coat the concrete to prevent the chloride ion penetration, the better you are. But out of 1.8 million components out there, a lot of those are already in place, and a lot of them probably had little to no preventive maintenance or initially applied coatings or protectant of anything of any value. So we have probably a lot of chloride already in the surface that we need to just try to minimize the damage until there's contracts to come by and do some type of reconstruction, widening, or something where it can be basically rehabbed.
I'm wondering if you can combine treatments and you use penetrating sealer, maybe like Potosil, and then do your coatings both? Are they compatible?
That'll vary manufacturer to manufacturer. I think you should be, yes, you should be able to, within a manufacturer, have particular silane or siloxane-based penetrant sealer, or even an epoxy penetrant sealer, if you so chose, that would penetrate into the concrete and then come back and put an epoxy-based primer or and urethane or an acrylic finish coat over it, belt and suspenders type of approach.
The preceding was produced by the National Center for Pavement Preservation. More information can be found on the web at pavementpreservation.org. Additional support provided by Michigan State University.